Yesterday we started this drag force problem, and I felt like we didn't quite get all the way through it. We didn't get all the way through it. I don't know why I said I felt like. We just didn't. I'm going to get through this, and then I want to talk about the homework. In working with a couple people before and after school, I realized that this homework, I think it's very, very reasonable, but the difficulty level of the problems didn't correspond with the order of the problems. Okay, so like some of the really hard ones were right at the beginning, which is crappy. So I'm going to rearrange that for next year. I'm going to try to get better about that, but I guess just for future reference, because this is just my second time working through this, it's going to happen again. As much as I try to plan ahead and make sure that I rearrange stuff in a cognizant fashion, it doesn't always happen. I'm trying to keep better notes this year than I did last year as I'm organizing through all this stuff. But so if you get stuck on a problem, fine. Just write down, I don't know how to do it, and then move on to the next one. Okay? And don't stress over it. Probably we'll go over it in class. Okay? So, anyway, so let's finish up this drag force problem. I had saved the progress that we did yesterday, but somehow I don't know what happened to the... Oh, I know where the file is. Oh, wait, no, that was just the video. Let's see. File. No. File. No. Open. Cancel. All right, I don't know. All right, are these numbers right? Is this where we left off for the values of these forces? I'm worried about the force of kinetic friction. Is this what we came up with? This is the drag force problem we were working on yesterday. It was 4.2, number 5, I guess it would have been. And I'm missing drag force. I know I got to put drag force on it, but... Yeah. Do I need to explain the mg over 4? Okay. Yeah, so we know that the block is moving, right? The problem tells us as much, right? That she's skiing and she's coming down the hill, right? So to find that force of kinetic friction, here was what I did. So we know force of kinetic friction is equal to our coefficient of kinetic friction times our normal force, right? So, the normal force we had found to be the same as this perpendicular component, right? And remember, this was what? Just mg times the cosine of 30 degrees, right? That's where the root 3 over 2 comes from. Cool. So, our coefficient of friction is 1 over 2 root 3. The problem gave you that. And then our normal force is root 3 mg over 2. Carly, good up to there? So the root 3's cancel, which was why I gave that coefficient of friction in those terms. And so you're left with the mg over 4, right? All right, so is everybody good up to here? All right, and then the one other force that we need to put in is our drag force. The drag force is magnitude kV, and then we just need to make sure our signs sort of line up the way we want them to. And this was what Sebo asked about right as the bell was ringing. So I just want to ensure that, so we decided we were going to make down the hill positive, right? Because the motion was going to be down the hill. Okay, so under those circumstances, let's see. A positive velocity would give me a negative drag force. So I need a negative sign here. My kinetic friction also is negative, right? Because m and g are both positive values. Follow? Yep. All right. So I think that was kind of where we had gotten to yesterday. Are we good up to that? All right. So to finish this dude, we're going to start with our classic, and this is going to come up more and more this year. Net force equals net force, right? I know it's a silly equation, but I actually, this is my first year using this, but I'm actually growing to like it quite a bit. So basically what it means is there's two ways to find net force. Mass times acceleration equals total force, right? So for us, that's Fg parallel plus FFK plus FD, right? Good? So I'm going to do two things here. I'm going to change my A to a, what? dV/dt. And I'm going to replace my forces with the actual values. So Fg parallel is mg over 2 positive, because it's going in a positive direction, plus my force of friction, which is plus negative mg over 4, plus my drag force, which is negative kV, right?
Yep.
Yes, Peter?
So if you already said this, but how did you determine like which direction was positive and which was negative? Is it just because it's going to the right? Or did you
It was arbitrary. So it doesn't matter which way you pick to be positive and which way you pick to be negative, but once you pick it, you've got to stick with it.
got it?
Do you know what I mean?
Yeah.
So I chose down to be positive just because that's the direction it was moving in. To be honest, I prefer, if you guys hadn't said that, I probably would have made down negative and up positive just because that's the way my brain works.
Right.
But either way, Maggie?
Wait, okay, you might have already made this.
That's okay. I don't mind repeating myself. It's all good. What do you got?
But yesterday, when you wrote the equation that was plus KV,
Okay.
plus KV's
I think I was rushing myself, and I think I may have made a mistake yesterday when I did it, because I think I was thinking, oh, it's up, so it's going to be plus. But, I mean, look, so as it goes down the hill, my velocity is going to be positive, right?
Yeah, I thought it was, you were subtracting negative KV, which is what you said.
Okay, I think I misspoke yesterday. That's part of the reason I wanted to rewind and go over this, because I was rushing. So, before I get you, Josh, Maggie, does it make sense why it's minus or no?
Oh, because it's just negative KV.
Yeah, I mean, basically I want to ensure that numerically I need to be adding a negative force, I guess, right? K is a positive value. The problem tells you that. If you're going down the hill, the velocity is a positive value, right? So I need to be doing plus negative kV, right? I heard a question mark and you're okay. What's messing you up? Is the drag force working with or against the motion? And so that's why I'm subtracting it.
Okay, then the problem say negative KV at the equals negative KV.
So why is it saying that? So
Because
because
it opposes.
it opposes the motion, right? So it's saying if your velocity is positive, then your drag force is going to be negative, and vice versa. So that's all that negative sign is in there for. Good? All right, everybody good? Anybody ungood? All right, so this would, on an AP test, this would be question A. Set up a differential equation which could be used to solve the velocity after time t, or whatever. Good?
Wait, so you would have to put L on the other side to isolate the VT?
I don't think it matters.
Okay.
I think as long as you have an equation that has dv dt in it
You're good.
that is accurate, you're good. And the next step is going to be solve it anyway, so you know what I mean? Like,
Yeah.
they'll check to see that you got it in there somewhere. Adam, did you have a question?
I was just going to ask if you should simplify it, but I was just
We're going to have to anyway. All right, so are we good? All right, so next, so on the AP test, it'll say, now derive an expression for the velocity as a function of time. We're not there yet because you guys are still learning your calculus. So for us, the next question is set up but do not solve the integral that would be used to solve it. Follow?
Yep.
So now we need to simplify and get all our dv's and v's on one side and all our t's and dt's on the other side. So first of all, mg over 2 minus mg over 4 is
MG over 4.
negative.
No, it's not.
Oh wait, no, it's mg over 2, right, yeah. So you get mg over 2 minus kv, right?
No, MG over 4.
Jeez, thank you. Thank you, thank you, thank you. mg over 4, wow, I'm struggling today. Minus kv equals m dv dt. Everybody good up to there? All right, so I guess I would divide by m at this point probably. So that you get dv dt equals, the m's are going to cancel, so you get g over 4 minus kv over m, right? Everybody happy? Okay. So basically, this g over 4 is the combined effects of gravity minus friction, right? Gravity's winning, but then we've got drag force to contend with, so that's why that's negative. Okay. All right, so now we need to rearrange this thing and get all of our v's on one side and our t's on the other side. How you do this is kind of up to you. My knee-jerk reaction is to make this into one fraction instead of two little ones. I don't know. I mean, I guess you could just divide by this whole mess. So you'd get dv over this mess equals dt. But I kind of don't want this whole mess in the bottom of my fraction, you know? So let's multiply both sides by 4m. Do you guys agree that that would kind of simplify things a little bit? I guess it's undoing what I just did here, isn't it?
No, if you just do 4, like if you do m over m and then g over 4 and then 4 over 4 and then kb over m.
Then you don't have to deal with that entire number.
Do you know what I mean?
Nope.
Can I do it for you?
Come on up, please.
Yeah. Okay. We're gonna try again.
Yeah, it's weird if you're not used to the smartboard. Oh, right, yeah. Yeah, yes, that's the same thing as what I was, yeah,
Then you don't have to multiply both sides.
right. Yeah, does everybody agree with that?
Yep.
That works, right? Yeah, that's the same thing as, yeah, okay. You did the same thing in different words. All right, so everybody's happy, yes?
Yes.
All right, so let's move the v's to one side and the t's to the other. So I'm going to get dv over gm minus 4kv equals,
4m in the numerator.
I was going to do 4m over dt, but whatever. Somewhere you have to have a 4m. Oh, nope, damn it. dt over 4m, sorry. Cool, thanks. All right, so everybody good with that?
Yeah.
And if you put the 4m in the numerator on the other side, that's fine. It doesn't matter. Yeah. You can. I would leave it as g though until the last minute. It just, yeah, it's easier to write. It'll make your life easier. All right, so is everybody okay up to here?
Yeah.
And there are multiple ways you could have done this. Like Carla said, if you wanted to multiply both sides by 4m and put that over here, that works. It doesn't matter. As long as you've got your dv on the same side as your v and no v's on the dt side. Good? All right, so now we're almost done. So the last step is now to integrate both sides. So, integral. Yeah, I guess you can pull your constants out if you want, but that'll come out later in the wash. All right, so what's my time doing? My time is going from 0 to t. What was my starting velocity in this problem? F minus. Let's see. Sally is skiing. She begins at rest on a hill. So our V naught here is 0. Please be careful. This starting velocity will not always be 0. It is in this one because it says she starts at rest. Okay? But if she had, had some sort of starting velocity, V naught, that's what I would put here. Okay? And then what's my upper bound? V of t. There you go. And you're done. All right? And then you guys will learn how to take that integral in your calculus class.
So we just leave it there?
So just leave it there, you're done. Eventually you need to be able to solve it. But for purposes of Friday's test, you're done here.
We get extra credit for solving?
No, because I feel like that gives, he asked if you could get extra credit for solving. I feel like that gives an advantage to the people who are farther ahead in math. This is math class. All right? Are we good? Problems. Is there anywhere where I lost people in this process? Okay, cool. So, let's move on then to the 4-6 assignment. Yes?
Yeah.
Okay, so here's my recommendation. So, all of these problems, you guys, were problems in which you had an object either being pushed or pulled by some force that was either above or below the horizontal. Yes?
Yeah.
All right? In working with people before and after school on these problems, the thing that I'm seeing across the board is the students who are coming in with these drawings that have both vertical and horizontal forces and that original force that's at a weird angle. No. All right, what I want you to do is draw that force that's at a weird angle, draw it, then split it up into components, then make a brand new free body diagram that uses just the components of the forces, not the, not the funny angle force. Does that make sense? All right, keep track of your letters, okay? So if you're not given a force, cool, call it F. If you're not given the mass, cool, call it M. If you're not given the acceleration, cool, call it A. All right? And make a free body diagram. All right? So here's what I'm going to do. Numbers 5, 6, and 7, I think, were probably the 3 hardest ones on there. If you understand 5, you'll understand 6 and at least be a good chunk of the way towards understanding 7. All right? And even though 5 is the hardest one, the initial setup requires the same train of thought that you need to do 4 or 8 or any of the other ones. Okay? So, as we're going through number 5 here, I want you guys to be not so much getting bogged down by the fact that eventually you got to do a little bit of calculus. We'll talk about that. But what I'm more worried about is that you understand the process up to the calculus. Okay? Because that's the step that you're going to have to do in all of these problems. All right? So here we go. So I'm going to do number 5, and then I'll take requests. Okay? So number 5 says, a box is resting on a rough horizontal floor, and it's to be moved horizontally. So draw it. Box, rough horizontal floor. The coefficient of static friction is 0.4. To start the box moving with the weakest possible applied force, in what direction should the force be applied? All right, so the idea is we're going to put a force on this box to try to get it moving. So let's assume we're trying to get it moving to the right. Good? So don't draw this, but just listen for a second. So the idea is I'm going to put a force on it. Oh, that's not what I wanted to do. Sorry. I'm going to put a force on it in some direction, right? And so the question wants to know what direction, oh, darn it. Well, not let me, oh, there we go. What direction should that force be applied in? Assuming a fixed value of F. All right? And so, first of all, why would the direction of this force matter? It seems like if I'm trying to get it to go horizontally, I would want to push horizontally. But what's the other variable? I want everybody to think about this for a second before I call on anybody. What's the other variable that's going to affect the motion apart from our force? All right, so now you want to get started? Friction. Okay, cool. So why does the direction that I push, what does that have to do with friction? Evan, what are you thinking?
Pull up to reduce.
Good. If I pull up a little bit, if I make my force go up a little bit, isn't that going to decrease my normal force? And decreasing normal force is good because that decreases the friction, right? Good? But there's a cost. Because as I increase that angle, what else am I doing? You're losing horizontal force, right? So do you guys see sort of the dilemma? So we want to maximize it. We want to figure out at what angle do I, sorry, I said maximize. We want to, so at what angle do I minimize the force needed to get the thing moving? Does that make sense? So what I want to do is I want to come up with an expression that tells me how much force I'm going to need to get this thing moving for a certain angle theta.
Calculator or non-calculator section.
The whole thing is calculated.
Oh, sweet. So this is fine.
Okay, so does everybody understand the question that we're trying to come up with? The question is, for a given angle theta, how much force will I need to get this thing moving? And we can safely assume that we're going to pull up as opposed to pushing down, right?
Yeah.
Does that make sense?
Yes.
All right, so what I'm going to do is I'm going to take this force F and I'm going to replace it with two components, Fx and Fy, right? Oops, that's not how you draw the letter Y. Fy. Follow? All right. Now, I want to express those in terms of the variables we're concerned about, which for us is f and theta, right? So do you guys agree that fx is just f times the cosine of whatever theta is? And fy is just f times the sine of whatever theta is? All right, so I think most people got that far. Is everybody okay up to there? Everybody good? All right, so what I'm going to do now is I'm going to make a brand new drawing. This one's garbage now because it's too cluttered. I got forces at angles and forces not at angles. I don't like that. New drawing. So I'm going to smallify this to give myself a little room to work with. Smallify, that's right. So here we go. Here's the rough horizontal floor. Let's see, what forces are there? Every time you make a free body diagram, you should always begin with force of gravity. Good? All right, and then my problem here tells me I've got two horizontal forces. So there's, two other forces. Fx is f times the cosine of theta. And Fy is f times the sine of theta. What's up? Well, I'm not done yet. Okay, so as Teddy just said, what other forces are there? There's a normal force, right? Don't just label it Fn. Tell me what the normal force is. So, my normal force has got to be big enough to make all my vertical forces cancel out. We can, I think, safely assume that this vertical force isn't enough to lift it, right? That the weight is more than that vertical force. So, that means that my normal force is going to be Fg minus Fy, right? Everybody agree with that? All right, take it one step further. This is then mg minus f sine theta. So why did I do that? Well, I want this normal force to be in terms of physical constants and the things that I'm interested in, which for us is f and theta. I've still got that stupid m hanging out. Hopefully that'll cancel out later on. All right, so is everybody okay with what I've done so far?
Yeah.
All right, now there's one other force that goes on this drawing. Friction. Now, if our goal is to get the thing moving, talk to me about that force of friction. What sort of friction should I be looking at? Static. Oh, give me a little bit more. Not just static friction, but the maximum, right? Because to get it moving, I have to overcome my static friction max. Follow? All right? And the force of static friction max, well, that's just, I say just all the time like it's trivial, and I apologize. I don't mean that to sound belittling. But our static friction max, that's the static friction coefficient times our normal force. Follow?
Yep.
So that's, let's see, our static coefficient is 0.4. And our normal force is that mess up there that's underlined in red. mg minus f sine theta. Good? All right, now, this drawing right here, you guys, is used to solve probably 70% of the homework problems. The only difference is sometimes the y component is down instead of up. And sometimes the friction is kinetic instead of static. But it's the same basic setup. All right? So if I want to get it moving, that means that this x force has to be bigger than this force. So set up an equation and solve it. Okay? If it's kinetic friction and I know the acceleration, then net force equals net force, right? But this drawing allows me to set up an expression for the right side of my net force equation. Follow? Okay. Any questions? I'm going to solve it. Yes. All right, so is everybody good?
Yep.
Okay, now, let's do this. I guess before I move on, because we're about to get calculus-y. All right, so before I get calculus-y, I want you guys to understand that none of this was calculus, right? And this is, like number 4 has a setup very similar to this. Number 8 has a setup very similar to this. Okay? With no calc. Okay? Yes.
Just go up just a little bit so I can see that in the equation.
Oh, this guy?
Okay.
Follow? All right, so the question wants to know what is the angle which gives us the minimum force? Yes? All right, so I feel like the first thing that I should do is I should come up with an equation that tells me how much force I'm going to need as a function of theta. Good? So, to get this thing moving, oops, that's not what I wanted to do. So to get this thing moving, my goal is I need this force to be at least as big as this force, right? So here we go. So I need my F cosine theta has got to be at least as big as my static friction max. Make sense? Any problems? I guess if we wanted to, we could have done net force equals net force. On the right side, we'd want our net force to be positive. And then on the left side, it would be F cosine theta minus this mess. So it boils down to the same thing. Good? All right, let's solve this train wreck for F. So let's see, this becomes, F times cosine of theta minus, equals 0.4 mg minus 0.4 f sine theta. So let's move everything that has f to one side. So f cosine theta plus 0.4 f sine theta equals 0.4 mg. Good? What can I do on the left side of that equation? Factor out f. Does everybody see that? The f is in both terms there? Too fast? Are we okay?
Good.
All right. So now divide. So you get this mess. So here we go. F, I'm going to change my notation a little bit. F as a function of theta, so this doesn't mean f times theta, it means f as a function of theta, is 0.4 times my fixed mass times g divided by this mess, cosine theta plus 0.4 sine theta.
Is that because everything is constant?
Yes, because the mass of our box is a fixed value. I don't happen to know what it is, but it's a fixed constant. And then G obviously is 9.8.
All right, thank you.
Did you just win an argument?
No.
Or lose? Or
I definitely lost.
oh, gotcha. Okay, so let's talk about that for a minute, because somebody was in before school talking about that this morning. Do you guys understand why m is not a quote-unquote variable in this problem? The box that we're moving has a chosen mass, right? We don't get to change that. The box has a mass of something. We don't know what it is, but it's a number. Cool? So this is one of those things, I know a lot of you guys like to just pick numbers. If you want, you can pick a mass of 1, I guess. I don't love it, because I'd prefer to see you working in terms of letters. But it works. You can pick a mass. The mass didn't matter, so pick 1 kilogram. Or 1 over g. You know? All right, so are we all good? All right, so now here's the deal. Here's where we get calculus-y. All right, and I know those of you in BC are apparently just learning how to do this. All right, so pause on this for a minute. Suppose I give you this. function, right? Oh, this is supposed to be a lowercase f. I wasn't trying to imply force. All right, so here's a function, right? So that function is going to, I don't know what it looks like. I legit don't know what it looks like, but because it's a cubic, that means it's going to go up and down. It's going to be something like this, right? All right? Now, in calc, one of the things you will learn how to do if you've not yet is you'll learn how to find a maximum or a minimum. All right? I can explain it to you super quick, though. Look. Anytime you're at a max or a min, what's the slope? 0. All right? So write this down somewhere in your like book of physics tricks. Anytime you're trying to find the maximum value of something or the minimum value of something, take a derivative and set it equal to 0. Does that make sense, you guys?
Yes.
Sarah, what did you just say? Yep. So anytime you're trying to find a maximum value of something or a minimum value of something, I'll let you write that down before I finish. So anytime you're trying to find a maximum value or a minimum value of something, you take a derivative, set it equal to 0, and I'm going to say sloppily, Sarah, so you're going to take a derivative, set it equal to 0, and then find x. That tells you the value of x where your maximum or minimum occurs. Good? Then how do you find the maximum or minimum? Plug that value of x back in. Yes?
For this problem, can't you just take your equation that you just made, like the whole f of theta, just graph it?
Yes. And use your calculator? Yes. And I was going to say that.
That's fine.
So, ideally, I would like you to be able to do it this way, because to me, there's more value in understanding the math behind it. Now, if your calc is a little sketchy or you're not super confident, you can absolutely graph it and then use your calculator to find a max or a min. And totally acceptable. Good? All right. So, does everybody kind of understand what I'm saying here? Sarah, are you good? Are you lying so I'll leave you alone, or are you good? Okay. All right. So, here, what I'm trying to do is I'm trying to find, instead of the value of x that maximizes f of x, here I'm trying to find the value of theta that maximizes force. No, minimizes force. Minimizes force. All right? So, we got to take a derivative. So, there's a quotient rule, right? Heidi, Lodi, something, D, something, something. All right, I will tell you a fact. I don't know the quotient rule. I don't know it. All right? I would write this as cosine theta plus 0.4 sine theta to the -1 and then use the power rule. Because I'm stupid and I cannot for the life of me remember the stupid quotient rule. And I know there's this Heidi, Lodi thing that it doesn't work for me. So, whatever. You guys all know the quotient rule, right? All right? So when you take the derivative of this, what you end up getting is you get something along the lines of the derivative of this, which is 0. No, I'm lying. Oh, wait, where am I? Oh, right. Yes. So you're going to get the derivative of this, which is 0, times the bottom, right? And then you're going to get this times the derivative of that, right? All over this bottom mess squared, right? Follow? So you end up getting, and the only thing is I don't remember where the negative is, but it ends up not mattering. So you're going to get this top mess, 0.4 mg times the derivative of this, right? So what's the derivative of cosine, you guys? Negative sine theta plus 0.4 times what's the derivative of sine? Cosine all over some BS that I don't care about.
Oh yeah, that's right. We don't care.
Why don't we care, Saba?
Because you can't, yeah.
Yeah, because if we're going to set this whole mess equal to 0,
Doesn't matter.
then the bottom doesn't matter, right? Because if A over B is 0, then A is 0. And B doesn't matter. Cool? All right. So what this tells us then is negative sine of theta plus 0.4 cosine theta equals 0. Oh, that means 0.4 cosine theta equals sine of theta. So what am I going to do now? Divide by cosine.
I like it, but it's hard.
All right, did I algebra too fast? So what's sine theta over cosine theta? Tan theta, and you guys can all solve that using your calculators.
Calculations.
All right, now listen. So technically speaking, all this does, so if you solve this, you get theta is, what's the answer, 21.7 degrees? So what that tells you is that there's either a max or a min at that point. Okay, which one it is, you guys will learn in calculus. You can take a second derivative and da-da-da-da-da-da. But in this problem, look, isn't that the only solution? That's the only solution to this equation, right? And since it's asking for a min, it seems pretty safe to me that we can assume that this is where the min occurs. That's a little sloppy. Technically, you should take another derivative and make sure that your second derivative is concave up, so positive. But whatever.
But for now, the number that we find there would be the answer.
Would this kind of thing be on the test?
I've seen stuff like this on
Or like on ours?
Oh, no, not yet. No. Okay. So eventually we're going to get to doing problems like this on a test, but until you guys get a little stronger with your calc. But I'm trying to, shh, guys, can we not text?
High fives.
Super. Totally lost my train of thought. What was I just saying? Oh, I know what I was going to say. So no, I would not put a problem like this on Friday's test. And I want to expose you to as much of it as I can now, so that when we get to actual, like, doing old AP problems, you've seen this stuff before. All right? Because eventually, you're going to have to know how to do this stuff for your grade in this class. Okay? So that's, we're getting there. Clear?
Clear.
7 and 8 are very similar to this.
Makes so much sense.
All right? Now, here's the deal, you guys. I don't know if this is a thing people say, but the meat and potatoes of this whole worksheet is this big drawing right here.
I think it's the bread.
Bread and butter? That's good. I don't really like eating potatoes. That's not true. All right. So this, you guys, if you're struggling with the assignment, make a drawing like this and go from there. Good? All right. We got, what, like 10 minutes, 8 minutes? I got time to take one request. We don't have time for all of them, but I will say almost all of them stem from this.
7.
All right, so real quick, I heard some votes for 7. Who wants to see 7? 1, 2, 3, 4. Oh wait, no, 7 is similar to 5. I want to do one that's not calculus-y, and 7 is calculus-y. 11? Who else wants 11? All right, 11 it is. Let's go. Oh no. Shoot, Oh wait, I think I just found it. Thank you. Okay guys, shh. 11. Yes, this is a good one. All right. Initially, stationary box of sand is to be pulled across the floor by means of... Oh, 11 is just like, it's exactly the same one we just did. You're trying to find the angle to maximize the mass.
Oh god, next one.
So that's calculus again. So how do I know just by reading it? What's the key word? Maximize. It says to get the greatest amount of sand. So you're trying to maximize the mass you can move.
So you have to get a function of the mass in terms of...
So you need to find a function for the mass that you can move as a function of the angle at which you pull. Okay? And the force that you pull with is 1100 newtons. All right, I want to make sure, so are there any sort of algebra-y ones that we should talk about? And I know I need to rearrange this. I'm sorry, you guys, I can't.
We should do an algebra because it's going to be on the test.
Like 8 is a good one, 4 is a good one, 3. Let's do 3. All right, here we go. 400 Newton block. 400 Newton block. What am I telling you? The weight. Number 3. It's dragged along a horizontal surface by an applied force as shown, and it gives you those two components, right?
Yep.
So I'm going to just skip right to this and say, oh, well, I know my fx is 4/5 of f, and my fy is 3/5 of f.
Oh, that's okay.
The coefficient of kinetic friction is 0.4. And it moves at a constant velocity. Find the magnitude of f. Constant velocity is super duper mega important. Why is constant velocity important? Because the net force is 0, right? Oh, that means that whatever my kinetic friction is has got to equal fx, which is the same as 4/5 f, right? I know something else about my coefficient of friction, or about my force of kinetic friction. So here's what we just decided. I just decided that my force of kinetic friction has got to equal fx, right? And I know because I took honors physics that my force of kinetic friction is that. Sorry, I didn't mean to single you out when I said I took honors.
I did all of this and I feel like I'm about to get it right, but I got 154.
Oh, that might just be a...
I got that too.
I think that's right. Last year I was trying to be careful about significant figures, and I abandoned it, I think, after this chapter, so I will fix the answer to...
Okay, so then I don't need this problem.
Okay, yeah. So I think it's 153.8 or something that it comes out to.
I got 0.8.
Yeah, and so I think I just sig-figged it, or sig-figged it.
That was really, I was like, oh.
Okay, so I'm sorry. All right, so...
Figures on what's wrong with this one.
All right, so let's finish it since we've come this far. So these two things are equal, right? So I get 4/5 f equals, our coefficient of friction is 0.4. Our normal force is 3/5 f. Wait a minute, what did I do? Oh! Dang it. Sorry. How did I let myself get this far off track? My free body diagram's wrong. What did I forget? I forgot my normal force. So my normal force should be 400 minus 3/5 f, right? Does that make sense? Sebo, are you good?
Sort of.
Where am I losing you? And then I'll come back to you, Carla.
So I have the same drawing. Let's just continue.
Say it again.
Let's just keep going.
Okay, Carla? Okay, so now I can do this. So my force of kinetic friction, I know that it's 4/5 f from here, and I know it's mu k times Fn from this. So this has to equal mu k, which is 0.4, times my Fn, which is this business here. So 400 minus 3/5 f. And then solve for f. And it gives you, like I said, like 153 or something like that, 154. Cool? All right, that sig thing messed people up, didn't it? All right, so I need to fix that. I apologize. What number is that? Number 3?
Yeah.
I won't lose my hand. All right. So, yeah, well, Harlan. So here's why. Shh. Carlo just asked a really good question. Number 4. Number 4 says if the coefficient of friction is 0.4, find the minimum magnitude of force he needs to start the box moving. And she said, does that mean we need calculus? And the answer on that one is actually no. Because the minimum force you need to get something moving means that your horizontal push has to just overcome your static friction, right?
How is that minimum?
Because your static friction is a fixed value.
I
But
thought before we were overcoming.
I know why you're confused. Let me see if I can think of a good way to answer this.
but isn't it at a different angle? So then that changes. Oh, that
No, because
goes
your angle's
fixed.
fixed.
Okay, that makes
Because
sense.
there's nothing else changing in this one, I guess. Do you know what I mean? Like, in the problem I just did, the angle was a variable.
Okay, that's fine.
Here, the only thing changing is your force. And so you just need to solve for what force will give you just enough force to overcome that static friction. So maybe I should add that as a caveat. I said before that anytime you see max or min, that's a sign to do calculus. And I guess that's not necessarily true. It's anytime you see max or min of one thing as something else is changing. Okay? Maggie?
Number 4, not the answers, but not the overall.
You must have made a mistake somewhere there. Hang on, let me stop the recording.